Okay. So we worked through some examples on practice exam A last class. Are there any specific questions that anybody wants to go over? Yeah.
Question 11, I think. I was just confused on how on the answer key you got the T-square.
Okay. So just kind of more generally, we'll start with that one. I want to kind of lead into it with a certain discussion. So I put up kind of a revised, going to be easier to read some of those formulas. So the formula sheet looks a little bit different now. This side still, everything's the same. Just kind of to like walk through it a little bit because I looked at all the responses to, was it Friday or Monday's kind of survey quiz. And just to kind of keep track of your formulas, right? Here, these formulas are going to be related to kind of when we have like just a normally distributed variable, right? Either a sample mean or a proportion. Here's if we're looking at confidence intervals for one population where all we have is the sample statistic and we don't know what the true population mean or the true population proportion is. Kind of notice the differences here. It kind of reminds you that if it's a sample mean and you're given a population variance or population standard deviation, you're using kind of that standard normal or the Z tables when you're calculating the confidence interval. When we have a sample mean where we only are given a sample variance. So anytime you see this word sample variance or sample standard deviation in the problem, if you don't, you should automatically be thinking that you're using the student t distribution. And the confidence interval equation here kind of reminds you of that. Right? If it's one population, that degrees of freedom is n-1. But if we go up here to kind of our two population confidence interval equations, it'll kind of remind us it's not n-1, it was that really complicated formula. I told you I'm not going to make you use that. So in any example you would see, I'm essentially going to give you that delta or give you that degrees of freedom, okay? Or like an assumed true degrees of freedom. Once again, similar idea. If you're dealing with proportions or you have sample means where you know population variances or population standard deviations, you're using that Z table. Anytime you only have sample variances, see that word sample variance, student t distribution. Right? You then have your test statistic equations. For those three different types of examples, once again, anytime you see proportion, I almost like write this down in a cheat sheet going into the exam. If I see proportion, I know those problems, standard normal distribution, right? If I see that word proportion, standard normal distribution. If I see anything with sample variance or sample standard deviation, right away, all those problems, student t distribution. I would maybe write those two things out going into the exam. That way it can help you identify which equation you should be working with. So here's our test statistic equations for one population. Here's our test statistic equations for two. The sample proportion, when you're looking at the differences, that equation becomes a little bit more complicated where we have to kind of calculate this p bar first. Other than that, that should kind of help keep everything kind of organized on this formula sheet. Also, kind of just a reminder, I just got this little table on here for if it's a right-tailed test, left-tailed, or two-tailed. It kind of reminds you when you find that area in the tail here, you need to multiply it by 2 for a two-tailed test. Another thing that I kind of want to show you because people were having difficulty with critical values. This might help kind of keep it straight. So whether or not it's a one or two population example, for a right-tailed test, right, we're thinking about our critical values will always be what? No matter if we have a standard normal or a student t distribution, they both would have a mean of what? 0. So anytime I'm thinking about a right-tailed test, my critical values will be positive. Anytime I'm dealing with the left tail or left side of the distribution, my critical values will be negative. And anytime I have a two-tailed test, I'm going to have critical values that give me a total of alpha in the tail. So on each side of those critical values, right, for a two-tailed test, you'll have kind of alpha over 2 in each tail, and you'll have a pair of critical values. Okay? You can think about here on a left-tailed test, all of alpha's in the tail. It's just you're looking at that left tail. And then for a right-tailed test, all of alpha is kind of in that right tail. So maybe writing it out like this reminds you, if I'm looking for a critical value for a two-tailed test, I look up alpha over 2. If I'm looking for a critical value for a left or right tail test, I look up just alpha. Now, left tail, it's alpha in the left tail. Right tail, it's alpha in the right tail, which makes my critical values positive for right tails, negative for left tails. Might be a way to kind of keep that, like have that written down going kind of like a little cheat sheet thing too, okay? So what's the equation to find the critical value? So I think there's just, some of the comments I saw too, I think there's a little bit of confusion, right? In that there's no real equation, right? So if I'm looking up a critical value for a left-tailed test, for example, and let's say it comes from the standard normal, it's going to be the value that gives me alpha in the tail, right? So let's assume, I don't know, alpha is 0.1, right? What I'm doing there is there's no equation. I know the area I want in the tail. I have to go to the table, look up that area. So in this example that I'm kind of talking about, I know the area in the tail, so I go and I try to find as close as possible to 0.1 in between these two values. So negative 1.28 and negative 1.29. So negative 1.29 would be that critical value that would give me alpha in the tail. Right? So there's no equation for these critical values, right? We're looking them up using those tables, or you know what you could have done. All my markers are starting to kind of die in here. So what you could have done is use, no, not this, .inv. You want the area of 0.1 in your tail. That equation in Excel would return you the critical value. Now, obviously, the answers are going to be displayed rounded to the second or third decimal on the exam. So, you know, in Excel, this will give you a 6 or 7 decimals. So you'll have to kind of do that rounding for yourself. But that would be kind of the same process we're doing there. Okay? And the student t distribution is the exact same way, right? Let's say this was a student t distribution. We still want the critical value that gives us 0.1 in the tail. It's just now we need degrees of freedom, right? So if we go to that student t table, I still want 0.1 in that tail, but I need to know what my degrees of freedom is. So let's say it was 10. 1.372 would give me 0.1 in the upper right tail, right? Which means negative 1.372 would give me 0.1 in that lower left tail. So if I looked at my critical value for that, for a student t distribution example, I don't remember what it was, like 1.372 or something that I just found. All right, so it's going to be a little bit different, right? And that's because we talked about these student t's have like a wider, they have a larger variance, which kind of means they're like more spread out, right? So we would need to get that same area, we would need a different value, not negative 1.29, but negative 1.37. Okay? So that's just kind of a general discussion, I think, about some of these things, keeping track of things. I think this, what I had up there with the critical values, would be a kind of a nice thing to have there so you can remember, you know, how to approach kind of different types of problems, okay? Someone had the original question. Okay, one second. Doesn't give you degrees of freedom. How do you determine what it is? So if it doesn't give you degrees of freedom, it would, the only way you would have a problem like that is if you had a one population example where you only had a sample variance, and there you know the degrees of freedom is simply n-1, right? If it doesn't give you degrees of freedom for a 2 population example, then you probably shouldn't be using the student t distribution. I'll have to give you that assumed true value, right? Well, I guess I don't have to. I can make you use that equation, and you could, you know, plug in everything and round it up to the nearest decimal, but I told you I'm not going to make you do that. Right? So the original question, before I went off on these tangents, was number 11, right? So confidence intervals, it's kind of the same thing. Confidence intervals, when you're looking up either that z or that t value, it's very similar to critical values because you know the area that you essentially want in the tail. So you look that up to find what the corresponding z or t value that would give you that is. Right? So here we want the 90% confidence interval. So alpha here is 0.1, right? We've got 30 dentists, and all we have is a sample standard deviation. Right? So see that word sample, we automatically think about which distribution? student t, right? Anytime you see that word sample variance or sample standard deviation, student t distributions. How do we find our degrees of freedom? If this is a one population example, just n minus 1, so 29. So you would go to that student t table, degrees of freedom 29. It's a confidence interval, so your alpha is 0.1, but what area do you want on either side of your interval? If I'm thinking about a confidence interval, actually I'll draw it up right above here, because it's very similar to a two-tailed test. I'm going to build my confidence interval around that sample statistic I found. I want alpha over 2 on each side because I want alpha outside the interval. It's almost exactly what we're doing with a two-tailed test. I mean, it literally is exactly what we're doing with a two-tailed test, right? We want alpha over 2, so we'll look that up. So our alpha was 0.1, so alpha over 2 is 0.05. So that's the area we want in the tail. Degrees of freedom 29, 1.699. So hopefully, that's what I did in the answer key. Oh, where are we? Yeah, right? So that's how I got that 1.699 that we plugged in to build that confidence interval. Was there any other question? Let me see the chat. I thought I saw another. Okay. Did someone else have a question as we're going through things? Any other questions that you guys want to kind of go over specifically, or? Yeah.
It's not really a question, it's just an observation, because I actually ended up using the Z score on that. I didn't get the exact same answer, but I got something very close to
It'll be close, right? So why would it be close? So if we look at the student T table, remember, as we get to higher and higher sample or degrees of freedom sample sizes, notice this last row is the standard normal values that give you certain areas in the tail. So for that same area in the tail, here, we'll do this one, 1.282. Well, if I have a degrees of freedom of 80, it's 1.292. Well, remember, if I looked this up in the standard normal table and I rounded up, I was using 1.29, right? So to the second decimal, yeah, a lot of these will be very close, right? But they will be a little bit, a little bit off if you use, the standard normal value instead of the student T. Yeah. Now, if I give you examples with smaller sample sizes, you're going to be quite a bit off, right? Like this is 1.7 or almost 1.8 once we get up to here. Right? So it is important that we're correctly identifying which distribution we use. So any other questions you specifically want to start out with? They don't have to be specific problems. They could just be general questions. I think sometimes those general questions are good. Nobody? Bueller? Okay. It's a good one I think we should go over. Hope this is the answer here. Stay on practice exam A here. I want to do, we went through this one. We did 18 last class, right? Correct? Okay. Or wait, did we do 18? Does anyone have it written down? I think you did? Okay. Okay, we did. Let's do practice exam B then, because I want to go through some more problems like that, because I think those will be the most beneficial. Let's see. Okay, let's do this one here. So I have kind of another similar kind of BMI one. So let's say we've got Indiana, Ohio, we're comparing their BMIs, and we've got the sample mean for Ohio is 29, sample mean for Indiana is 28. We have the sample sizes for both states, and we have these sample variances. So sample variance, I even give you kind of the notation here. Automatically, what distribution should we be thinking about? Student T, right? So what would my degrees of freedom be? I should have taken this problem off here. I told you I'm not going to make you do this, right? So we can kind of skip 16, right? What is the 95% confidence interval for the difference between Indiana and Ohio? So this one, right, if we know that we've got two sample means, we're looking for the difference in sample means, and we want a confidence interval. Here's our two population or our kind of differences confidence intervals. Right? I've got sample means. I don't have the population variances. I have my sample variances. So this even reminds me to use that student T. Right? So I can plug in those sample variances, plug in those sample sizes, plug in the 2 sample means that I found. The only last step for a confidence interval is finding that t-value, okay? So we go back. We want the 95% confidence interval, so our alpha is 0.05. Right? Our assumed degrees of freedom that we're given, right, is 50. Okay? So I know that my degrees of freedom is 50, and I want 0.05 divided by 2 on either side of my confidence interval, so 0.025. So I'll go to that student t table. I want degrees of freedom of 50, and I wanted 0.025 in each tail, the area in the tail, so 2.009, right? So I'll go back to that formula, I'll plug in 2.009, add this margin of error, which is what we're calling what's on the right-hand side, to get my upper bound, subtract it to get my lower bound. Now, for the sake of time on these, what I would suggest, this one has repeated answers, so this is a bad example. Let's say I probably just ran out of different ways. So let's say something like that. Once I calculate the lower bound here, I'm going to be able to identify the correct answer, right? So you don't have to calculate the lower and the upper bound if you don't want to, just for the sake of time. And if maybe want to go back to that one, if you have time at the end to double check and calculate the upper bound as well, that's one way I would approach, because once you find one of these upper or lower bounds, you can identify what the correct answer is. And actually, I didn't have kind of repeated here. I guess these technically were different. Now, if I think about, can I rule any of these answers out pretty quickly? Well, my first group, I found 28. My second group, 29. I want the difference for group 1 minus group 2, or Indiana minus Ohio. So the sample difference I found was -1. Right? What I'm doing with this confidence interval is basing it around whatever the difference in those sample means was. Right? So this is -1. I wanted 0.025 kind of on each side of it. Right? And that's how we looked up what the t-value would be. We almost think about it this way. I was wanting to go a certain number of standard deviations to the left and to the right. And the number of standard deviations to the left and the right I need to go to get alpha over 2 on each side of that confidence interval is whatever that t-value is. Remember, z and t-values are the number of standard deviations away from kind of the mean, right? So if I'm basing it around -1, -1 better be exactly in the middle of all those confidence intervals. So I go back here. I don't think we can actually rule, we can rule out B, right? -1 is way closer to -1.4 than it is to 1.48, right? Positive. So we could rule that one out. Don't think we can rule, we could actually rule this one out. It's a little bit harder to see, but -1 is a little closer to -1.7 than it is to 0.2. And it's smack dab in the middle of this one. So A or D are the only kind of possible answers there. Okay? Now, you don't have to do that process, but if you for some reason couldn't get the compute right, at least you got a 50% chance if you were guessing now instead of a 25. Right? So with the same, and this is how the exam will kind of be, I'll give you some information and you'll use it for like a block of 4 or 5 questions, right? So using the same information, what's our test statistic? These test statistic ones should be fairly easy. I mean, given that we can identify a problem as either a proportion problem or a sample mean problem, because even if you don't treat it even if for some reason, notice, I think that I've got a sample mean problem with population variances, once I plug the numbers in, it's going to give me the same answer, right? Right, for the test statistic. So I use this equation though because I only had sample variances. I plug in my sample variances, plug in my sample sizes, plug in my sample means. The only thing I'd be careful on problems where you're calculating these test statistics, make sure if you're given the variance, that's this entire numerator, but if you're only given the standard deviation, you would still need to square it here, right? So this is really just kind of a matter of getting these plugged into your calculator or plugged into if you're using Excel as a calculator, getting that plugged in correctly. The one kind of way you can safeguard from identifying really bad mistakes is we said, well, we're trying to find a test statistic, right? And we've got this assumption that it's greater than or equal to 0, then really what we could think about is when I've got the assumed true difference for my sample means is 0, and the sample difference I found, we said was -1, right? That's what we had. We had already done that for the confidence interval part. Well, if I find something below that assumed true value, I know that when I turn that into either a z or a t value, doesn't matter what kind of problem. Here we've got the student t distribution, so it's a t value. I know automatically, right, because whatever that assumed true difference is, right, it would have like a t value of 0. So if I see something below that, I know that I'm going to have a negative test statistic. If I see something above it, I'm going to have a positive test statistic. Right? And really that comes from the equation for the test statistic because, or it would remind us of that because, this denominator, remember, represents a standard deviation. In each one of these test statistic equations, the denominators always represent standard deviations. Here it's the standard deviation of a sample mean. Here it's a standard deviation of a sample proportion. Down here it's a standard deviation of the difference in sample proportions, and here it's the difference in the, it's a standard deviation for the difference in sample means, right? So your denominator is always positive, so here, whatever sample difference we find, that's gonna kind of dictate what the sign of the test statistic is, right? So, we can plug all those values in. I won't walk through those steps because I really can't give additional instruction. Once you identify those pieces of information, you're just plugging them into that equation. Right? But we said it has to be negative, so right away I can rule out B and C here. All right. Once again, if I'm having difficulties or I'm doing something wrong on my calculator, at least I can get this down to a 50-50 guess by just remembering those principles. Okay? So we plug all those numbers in. Let's see, we would get, so -1 divided by the square root of 9/40 plus 16/50. So -1.35 would be our test statistic there. Now, quite often at this point, what I would then do is say, well, look, if you got the test statistic wrong, I can't ask you any other questions about critical values and rejection decisions or p-values because you'll get those wrong as well. So I say use that same hypothesis test from 18. So what type of tailed test do we have? We look at the alternative hypothesis. Yeah, it's a less than sign. So we have a less than or a left tail test. I then give you kind of not only the assumed true degrees of freedom, but also assume the test statistic you found was -1.55. Right? So we've got a test statistic. We want to find a critical value and then make the rejection decision. So that critical value is going to be what gives us alpha in the lower left tail. So our alpha here would be the 95% confidence level. Alpha is 0.05. We're at the 5% significance level is what we're using. So we're thinking about, we have this test statistic of -1.55. We want to know, well, I probably shouldn't plot that first, sorry. Let's say we first want to find the critical value that gives us 0.05 in this lower left tail, right? I had that assumed true degrees of freedom of 50. So I go to my student T table. I look up degrees of freedom of 50, and I want 0.05 in the tail, 1.676. So that's my critical value, right? What am I forgetting? So this is 1.676. It's a left tail test. It's that value but negative, right? We can use that T table, but it's always kind of giving us the right side of the distribution. We were dealing with the left side here. So there's our critical value. You kind of think about, here's our rejection region. Anything to the left of it for a left tail test, right? Or anything more extreme than our critical value, larger in absolute value. We then go ahead, we plot our test statistic, which was -1.55. That would be kind of like right here. So that was our test statistic. Not quite in our rejection region. So the critical value is -1.676, and we failed to reject, right? Because our test statistic was just barely outside that rejection region. Okay? So what? -1.676, and we fail to reject, or we do not reject. Okay? Any questions over that? what if I had said, I gave you that same test statistic, but I want you to find the p-value, right? So you've got this test statistic. The p-value is the probability you saw that test statistic or anything more extreme, right? So kind of that shaded blue area, which is now almost purple, is your p-value. Right? So we go to the student t-table, right? We can look up 1.55, right? Positive 1.55, but the area to the right of that would be the same as the area to the left of negative 1.55. So our degrees of freedom, well, we can't exactly find that value. All we can do is put a bounds on that p-value if we wanted to do it this way. So I'm in between these two values, right? 1.55 is in between these two. So my p-value is going to be kind of somewhere in between 0.05 and 0.1. So greater than 0.05, but less than 0.1. Right? So if it's less than 0.1, I can reject at the 10% level. Right? If it's greater than 0.05, I can't reject, right? Because we only reject if the p-value is less than alpha. It's another thing you might want to write down going into the exam, right? We only reject when the p-value is less than whatever alpha you're looking at, okay? I think that should kind of get that batch of questions there. Any other questions? I mean, I can keep going. I just want to make sure I give opportunity if you have questions over anything specific, or even just like a general, like how do you approach this? I can kind of come up with problems off the top of my head as well. Just want to see me keep choosing some. I last class kind of put up, we went through how to categorize like which ones we use the student T and the standard normal. Hopefully kind of the discussion I gave today also helped. But if we're thinking about a problem like this, so which of the following would use the standard normal distribution, and, not the student T? If we were doing confidence intervals or critical values or p-values, so confidence intervals or hypothesis tests where we have two means and the population variances are unknown. Once again, if population variances are unknown, all we have is the sample variance. We use the student T, so we don't use the standard normal there. One population mean where we have an unknown variance. Once again, unknown population variance, so standard normals there. Kind of these match pairs ones we haven't really talked about. This was kind of material that I ended up kind of holding off on waiting till after the exam. And then confidence intervals for a hypothesis test regarding two population proportions. Anytime we see that word proportions, we should know standard normal distribution. So that's going to be our answer, right? Yeah, we wouldn't have, I won't have something like that in the exam this C. I was kind of using some old questions that I have used. Yeah.
I have a question on 15. You said the answer was 10%, 5% levels. So like once you rejected the null hypothesis at those levels, we have to reject it at the 1% level.
So this is a good thing to kind of keep track of. So I'll show you with both approaches why that's not true. So if I've got, let's say my p-value is 0.02. Right? So this is my p-value. And I only reject if it's less than alpha, right? So is that less than 0.1? Yep, so I reject. Is it less than 0.05? Yeah, so I can reject. Is it less than 0.01? So I failed to reject, right? So it's kind of like the problem that you're referencing. The p-value would be around that. Now, what you're thinking about is, remember, we can convert these are significance levels, but we can think about them as confidence levels. So this would be 90, 95, and 99. So if I can reject with 90% confidence, that doesn't necessarily mean I can reject it with 99%. Now, if I have a p-value that's something like, well, I'll leave this up here, 0.003, well, if I check it against the 99% level first, and I say, well, it's less than 0.01, well, if I can reject it with 99% confidence, of course I'm going to be able to reject it at the lower levels, right? Which makes sense. If 0.003 is less than 0.01, it's definitely less than 0.05, and it's definitely going to be less than 0.1. So if you can reject with 99% confidence, you can always reject at the lower levels. But if I can reject with like 90, that doesn't necessarily mean I'm going to be able to reject at higher levels. Yeah. But you're right, like on this one, I really only had to check it, because once I know I can reject with 99% confidence here, I know I can reject with 90-95. So in fact, if you even look at those answers on 15, so only the 5 and 1% doesn't make any sense at all, right? If I can reject at the 5 and 1, I definitely can also reject at the 10% level, right? The other ones are possible answers. I could only be rejecting at 10. I could only be rejecting at 10 and 5, and I could reject at all. But this one here wouldn't make any sense. Or if I said like only reject at the 1% level, it doesn't make any sense. If I can reject at the 1%, I can reject at the other two. Any other questions before I kind of maybe pick and choose a couple? Here we go. Calculating a test statistic. Yeah, so right, our test statistic equations, I pointed them out on the formula sheet here. So we've got our 2 population test statistic equations, and then we have our kind of 1 population, right? In terms of like, can I give any advice on how to do these? I mean, really, once you've identified what the correct test statistic equation is, and really you do that by looking at what is the problem given me. Once again, if it's giving me a sample mean and I know the population variance, I use this guy. Sample mean and I know the sample variance, I use this guy. Right? The components, I mean, you're always going to be given in the problem the variance, sample size, and sample mean. The only other thing you have to identify is what's the assumed true mean, and that will come from the null and alternative hypothesis. Now, on the practice exams I gave you here, if you identify it wrong here, you might make some mistakes, kind of have some cascading errors. So on the exam that you'll take, a lot of the times there'll be like a question 12 here where it asks you to identify the null and alternative. But then when it asks you to find critical values, I'd give you some new, assume we want to do this null and alternative hypothesis instead. So that way, if you identified it incorrectly, maybe let's say I thought it was a left-tailed test, but it was actually right. Well, then everything's going to be wrong after that. So I'll give you kind of what the actual, an assumed true null alternatives. And from there, whatever values in your null and alternative hypothesis, like if it was 105 here, that's what I'm going to then be using as my assumed true mean. Right? Same kind of thing. And then if I see a proportion example, I know that I'm going to be using this test statistic equation. Right? And those words are in the, when you see those questions, the words will be in the questions. For example, I mean, here I'm telling you, we have a sample mean and a population variance, right? So that I can identify what test statistic I need to use because I have a sample mean and a population variance. Okay, so it's this guy right here. Right? Or I have a problem that says I'm looking for the differences in between, and I guess I don't explicitly say proportion in this particular problem, but I'm giving you the notation. That might actually be even easier, right? Because now you see that I have proportions here, right? And I've got kind of, there's a little typo here. I guess I'll address this. Right, this should be group 2 here, right? I have the notation wrong. But you have these sample proportions. So I've got 2 sample proportions. I'm going to have to use this test statistic equation, right? And this is the one that required kind of that intermediate step where you first calculate P bar, but it's the same components, just the sample sizes and the sample proportions in it. Right? As far as like more advice other than like being able to identify the correct test statistics, it might be easier if you're doing this in a calculator, maybe first calculate what this denominator would be, right? Like break it down into steps. So if I first calculate what my denominator is, right, instead of trying to enter it all in at one time, that can sometimes help from making mistakes if you're just talking about, when I'm trying to calculate this test statistic in my calculator, I'm getting the wrong answer. Maybe breaking it down by finding the denominator first and then kind of plugging that value in and finding your test statistic, that can help. But in terms of identifying it, like here, I'm giving you sample variances, like I'm giving you the notation, sample means and sample variances. You have two groups. So when you go to that formula sheet, okay, here's my test statistic equations, right? I've even kind of grouped them here. So for 2 population, here's my test statistic equations. Sample means, sample variances. That's the one I'm going to be using. Is that making sense? I don't know if that completely answered the question. If it didn't, then you want to be more specific. But like in terms of like calculating it, I mean, once you have identified the problem, like at that point, it's getting it kind of entered in your calculator correctly. And if you're having difficulties with that, sometimes, like I said, breaking it down into parts can help. Any other questions? Okay. Well, which one would be good for us to go over? Is this A or is B? I want practice exam. So we'll look at B. We'll work through this proportion one. Well, I want a little bit more. Actually, I want to hammer one. Let me see. Is there an example? Okay, so we didn't go over this one. So like on 12, so we're given this information about you've got a population variance and you have a sample mean, right? So right away, just to kind of review that, if I have a sample mean, but I know the population variance, I should be thinking about which distribution. I know the population variance, so student T, the only time you should ever use a student T is if I see sample variance, right? I only have a sample variance. I don't know the population variance. Okay? So I don't have a sample variance here. I have the actual population variance, which maybe I could even use the test statistic equations to help me remember this. I have a sample mean and a population variance. Remember, the population variance is sigma squared. Sample variance is S squared. So I'm like, okay, this is my test statistic equation. Okay, I'm using that Z table, all right? So I should be using that standard normal distribution. If I want to identify null and alternative hypotheses, so whatever you're trying to find, whatever you're trying to test for, that's what your alternative hypothesis is. I'm not trying to necessarily, I'm not trying to trick you in any of these. If I want to test for whether the average IQ of a Ball State student is different than this national average of 105, right? Well, I'm wanting to test against that value of 105 then, right? Is it different than 105, which is really saying, is it anything other than 105 or not equal to 105? So not equal to 105 is my alternative hypothesis, which means I assume the opposite is true, which is that it's exactly equal to 105. Okay. So there'll be a couple questions where you're asked to identify what the null and alternative hypothesis are. Whatever you're testing for, whatever like the questions, like I said, I want to test if it's less than this value or greater than this value or different than this value. That's your alternative hypothesis. Excuse me, you then assume the opposite is true for your null, okay? So if this was kind of different than, right, we have a not equal to sign, what type of tail test do we have? One or two-tailed? Two-tailed, right? So, because I have a not equal to sign in the alternative hypothesis, I have a two-tailed test, right? So how would I find the critical values? We already said we're using that standard normal distribution, right? So what I'm thinking about is, if I want to find critical values for a two-tailed test, it's going to be a pair of critical values, right? It's a two-tailed test. And they're going to give me a total of alpha in the tail. So if we do the very first alpha of 0.1, I'm going to have alpha over 2 kind of in each tail here, which would be 0.05. Standard normal distribution, right? So I can use the Z tables, or I think I did this last class I went through and showed you. I'm going to cheat. So I want 0.05 in the tails. I'm just going to go to the very last row of that student T table because it told me what the standard normal values would be, right? Because a student T distribution with an infinite degrees of freedom is the standard normal. So I go down here and find 1.645. I have a pair of critical values. So once I look up the very first alpha, notice in these types of problems, even though you're finding like all three, I can kind of stop. I know that B is the answer now, right? I can identify that B is the correct answer. And if I had a two-tailed test right away, I should know that I've got a pair of critical values, right? the same value, but one's positive, one's negative. Right? So right away, I could have ruled out two of the answers. And then from there, I think the difference really was, this is what we'd find if you treated it as a student T distribution example, which you shouldn't have been doing because we had this known population variance. Okay. So we've got those three pairs of critical values. Another kind of nice thing, if we use this last row of the student T, I could have looked up, well, alphas of 0.1, 0.05, and 0.01. But I had a two-tailed test, so I had to divide all of them by two. So 0.05, 0.025, and 0.005. I could have went down, used those columns, and found the critical values all pretty quick. Right? So 1.645, positive and negative, 1.96, positive, negative, 2.576, positive and negative. Okay? Any questions on that one? Okay. So here's another one where we're looking for a test statistic. Right? So I go back, I've got a one population example where I have a sample mean and a known population variance. So I go to that formula sheet, sample mean. Oh, but I know the population variance. I know sigma squared. So this is my test statistic equation. I was given the sample mean, sample variance, and sample size. I plugged those in. The assumed true mean came from that null alternative hypothesis, which was 105. Right? Now, one way we could actually rule out some of the answers here as well is if I was assuming, so I have these sample mean distribution, right? And I assumed that it was 105 was the value in that null alternative hypothesis. The sample mean I found was 109. I know that my test statistic, if I was to turn that assumed true value into a z value or z statistic, it would have a z statistic of 0, right? Because our standard normal distribution is centered around 0. So my test statistic has to be positive, right? It's going to be something that's to the right of 0. So anytime I find something above the assumed true value, it's going to be a positive test statistic. So right away, I know it's either B or C. Right? From there, it's just a matter of getting those values plugged into that test statistic equation and kind of making sure our calculator, do our work correctly in our calculator. So let's assume that instead we found a test statistic that was negative 2.3. Right? So notice here, when I give you these assumed true values, the answer for the actual test statistic was positive, and I gave you a negative assumed true value. So once again, evidence, don't read into these at all, right? So negative 2.3, and I want to find what levels I can reject at. Well, what I could do is plot these critical values, if I was pretty confident in them, and then plot my test statistic and see if it's in any of these rejection regions, right? So I'll show you that way first. Oh, if I hit the stop share button and not minimize. So we had critical values here of positive and negative 1.645, positive and negative 1.96, positive and negative 2.58. And then our kind of rejection regions, right, or anything that are more extreme than those values. Okay. So where would that test statistic of negative 2.3 fall? Somewhere like here. So it's in the rejection region for the 5% level. It's in that rejection region at the 10% level, but it's not quite, right, in that rejection region for the 1%. So here we have another example where it's 10 and 5% only. Okay. If instead I wanted to find the p-value, or use that p-value approach, I'll find the p-value was the probability I saw the test statistic that I did, which was negative 2.3, or anything further away from that assumed true value. So it would kind of be like this shaded black area is my p-value. But remember, we had a two-tailed test, so what am I forgetting here? That area is not my p-value. It's only half my p-value, right? Because it would have been equally as likely for me to see a test statistic of 2.3, and that evidence also goes against the null if it's a two-tailed test. So for a two-tailed test, I'll take my test statistic to find the p-value, I'll look for the area that's more extreme than my test statistic. But then I have to remember it's only half of it, so I need to multiply it by 2. Right? So negative 2.3, I'll go to my standard normal distribution table. Negative 2.30, since it's 2.3, so negative 2.30, 0.0107. I then multiply that by 2, it's 0.0207, right? So 0.0207, I could then say, which of the levels is it less than? Well, we already kind of walked through that because you had that question earlier with the p-value, but 0.02 is less than 0.1 and 0.05, so we rejected the 10 to the 5% level, but we failed to reject the 1% level, which is the exact same decision that we made when we used the critical value approach there. And so either you could have used either one, came up with the correct answer for that problem. Okay. Any other kind of last minute questions like about the exam or one thing I did want to mention, I can't remember if it was this section. Someone asked if they have there shouldn't be any problem when you're uploading files, but if for some reason there is, just email me whatever the files were like immediately, right? Like as soon as because I can see when you did the exam, so don't send them to me like 3 hours later because then I could have been working on the entire. So if you think there's an issue with the file upload, make sure you kind of email those to me directly, right? If you haven't, like I said, the reminder is on once you open it, use Chrome, Firefox, or Internet Explorer to avoid kind of any issues not seeing certain equations or certain answers that kind of I had to use the math tool in the Canvas. Other than that, make sure you're kind of doing keeping to academic integrity, like work on these on your own. I'll be looking pretty carefully at the short answer questions that are kind of uploaded. Other than that, if you have any last minute questions, I don't know how available I'll be kind of over the weekend, but I'll try to kind of get some responses as you're maybe working through those practice exams. Other than that, are there any other questions for me? Okay. All right. Good luck. Have a good weekend, and I'll get this kind of uploaded as well, so we'll have the problems you worked through today on YouTube as well. Oh. Correct. We didn't reject at the 1% level because 0.02 was not less than 0.01. That is correct. Yeah.
I was just wanting to double check this because I am like doubting myself now with this. So for like the sample, you said use the t-value instead.
So this is right.
Okay.
Right. Because you're using a proportion.
Mm-hmm.
So it's not. So anytime you see proportion,
okay.
Z.
Okay.
Anytime you see the word sample variance,
okay.
or
T.
sample standard deviation, T. Yep.
Okay. So like for these.
So that looks good.
Like they said like sample, but is that
Yep.
going to be Z?
So that's
instead?
T. Nope. You're
Okay.
right. You're right.
Okay. So I didn't.
No,
mess it up.
that's perfect.
Okay. Awesome. Thank you.
Yep.